Okay, so let's get started. On Monday, Onuroj has already started the discussion on signals. Okay, and we look at them. See this. Okay, so with the signals, let's work to see if I can. Cannot see my mouse. Just wait a second. Just give me a second. Okay, so we had Onuroj started discussing the signals and what are signals. I want to refresh your mind about it so that we can go ahead and finish this. So signals are a simple form of inter-process communication. Okay, and it's, if you wish, it's just a binary information. You may, I like to think them as kind of a switch, okay, which can go up or down. This is like an electric switch, right? A zero or one, and it's sent from one process to another one to indicate that some event has occurred in the system. Okay, now you can note that the signals is essentially similar to interrupts in hardware, because in hardware, that it's something happens, some data arrives into a network card, somebody presses the keyboard. Okay, all those things appear as a hardware interrupt, whereas the signals are the software equivalent of this mechanism. So it uses the same system, and so this shows you, for example, that this, I have two different processes, process A and process B. Okay, and for each of them we maintain a set of signals. So for example, I can look at that. I have this signals for A. Okay, and it has a fixed number, and with them then we can have these, say, signal 0, signal 3, 4, 5, and 8. They are set. Okay, and then I also have signals for B. Okay, so you can see that for each process I have a signal, um, a set of signal bits. Okay, and when through this, one process can send another process a signal such that it will take a certain action. So that's the general idea. Okay, so it's similar to interrupts, as I said, and usually its signal type is identified by a small integer. Say it's 1 to 30. You can see that this is, everything is kind of kept in approximately 4 bytes. Maybe this is different in different systems, but what you have is you just have 1 bit per signal. Okay, and the only information is that you have your ID, which you can determine. As I said, you have this signal kind of signal information, and we have a lot of these bits. Okay, and based on the position of where you find the signal set, like a 1 1 here and 0 0 0, etc. Okay, this tells you basically which type of signals it gets. Okay, and so most of these signals may cause termination. Okay, but it can also block the process, or you can define a handler or ignore them. Okay, and you already know the sig kill or sig stop as an examples of this. So these signals are described by Onroja, so I will basically skip this and basically just move on to here. So what we do is, when you have different processes, the kernel, the sending of the signal is done through the kernel. Okay, so sending a signal is essentially a system call. So within your process, you can send a signal to some other process. Okay, and what you actually do is, for that particular signal, so if I have, say, a process P1 here, and I have another process P2, they both have these signal bits here. Okay, so if P1 wants to send P2 a signal, then it makes a system call, and through the system call, then it sets some basically bit in this signal set to one. Okay, and then this is basically what we call as sending a signal. Okay, and these signals can also be initiated by a hardware event. Okay, and so you can, for example, signal this is floating point error, segmentation fault, because you try to make a, say, null pointer access. Sig, I think this is illegal instruction, I would say, or it can be an operating system event, like like whether this is related with the pipes, this is a hang up, this is related to the child. Well, you have to read them, okay, and or you can use, for example, a kill system call. So we have this in the case of PCB, which was the process control block. It basically stores the signal's delivery status and is set up for the process. So we're talking about a bitmap, meaning that each signal is essentially a bit per signal. And we have a couple of terms that you should be aware. One is pending, the other one is block. Okay, when we say pending, it means that the signal is sent to the process. Okay, but it's not yet processed. Basically, the sender, for example, take this case of P1. In this case, when you set this, now this is the signal is sent, but the action that's related for this particular signal is not taken yet by the process 2. Okay, so in that sense, it's basically set as pending. Okay, or in some cases, the signals may be blocked. Okay, and the process, and we will see how we can do that, can decide to block certain signals, okay, because it doesn't want to deal with them. So let's look at them in detail. So here we have, different processes. And as I said, for each process, like, there can be some, like if this is my bitmap, some of them can be pending for A and some of them can be blocked for A, okay? And what you do is, when you want to send, for example, process A is sending, say, process C a kill signal, okay, then you basically set this particular signal to 1, pending for C. And then, after some time, and we will see when that happens, it's usually right after a context switch to process C, then its corresponding handler is executed and hence it's processed, okay? So, as I said, the destination process, it receives a signal when it's basically forced by the kernel to react in some way to the delivery of a signal. Okay, and when we talk about the signal handling, there are essentially three possible ways to react. The first thing can be ignoring, meaning that doing nothing. Okay, and the second one is termination. The process, for example, this is what happens when you have a C kill or control C, etc. And the third one is catching a signal. This is essentially you catch the signal, and upon this, you execute a user level function that's called a signal handler. Okay, and this is similar to a hardware exception. Okay, a hardware exception uh, which you execute in response to an asynchronous interrupt. So when we have, like in the case of a process, when it gets a signal, then from this your current instruction, then the control passes to the signal handler, and you execute the signal handler, okay, and then you return to the next instruction, okay. If you
Hocam,
can
in all three cases, Hocam, in all three cases, ignoring terminating and catching, all of them has execute signal handler, right? The
yes.
process below, the steps below are true for all the cases.
So that's like if you are terminating process, then this part is omitted, for example, right? But
Okay,
in
but
all
ignoring,
cases, there's this default, and in the case of ignore, it means that you're executing no handler. I mean, you just
okay.
pass from here.
You can mask signals actually. So if you mask a signal, that means even if you get the signal, nothing will happen. No handler will be called. It just gets ignored. So you don't have to define an empty handler just to do anything.
So let me just move on, and I'll take more questions if you still have. Okay. So as I said, a signal can be pending, meaning that somebody sent a signal, but that signal is not processed by at the receiver end. Okay. And note that in the case of a signal, this is why it's important that signal is a binary information. That the signals that can be are not queued. So what you're talking about is if I have a process C2 here, it has this basic mask, and then this is corresponding signal 0, signal 1, signal 2, and etc. And sending a signal is essentially setting this to 1. Okay. And if you send the signal again, okay, then, well, guess what will happen? It will again set this to 1 and nothing. So it means that, even if you send two signals, if they arrive before it's processed, then it will appear as a single signal. Okay. So that's why we are saying that the signals are not queued. We are talking about just one binary information. Okay. And this is again, like if you, of course, if you're talking about, this is signal 3, 4, 5. If you send another signal 5, for example, then it will be different. Okay. But keep in mind that we are not looking at the queue. We are looking at the bitmap that is being set. And a process can also can block the receipt of certain signals, meaning that in this case the signals will be delivered, but it will not be received until the signal is blocked. What this means is, for example, in my case, when I'm listening to you, say that I'm talking about some information, something, and somebody raises his hand, that's a signal to me. Okay. But I will maybe I'm doing something that's important. What I would do is I would just listen to I would not handle that, basically raising your hand, okay, until it's the right time. Okay. Or sometimes I can just block the receipt of certain signals because it's I prefer to do so. Okay. And typically when you have a signal, when it's executed, then this 1 is removed, and then it will set to 0 again. So each time you run a signal handler, you clear the corresponding bit for this. So essentially what we do is, like, the kernel, it maintains 2 bit vectors, pending and blocked, okay, for each process. So we'll have that, here's the, the pending, and here's the blocked. Okay. And so we have these corresponding ones. Okay. And pending means somebody sent the signal, but it's not processed yet. Okay. So it's essentially the kernel sets the bit K if you want to deliver a signal type of K, which corresponds to the K bit here. Okay. Then you set this to 1. That's it. That's simple. And when this the corresponding handler is executed, then that particular signal type is then cleared. So after doing this, then it's cleared to 0. Okay. Then we also have a blocked bit vector, which again can be set and cleared by the sigproc mask function. It's also known as the signal mask. And what this says is, in this block case, I can say that, for example, these, if I say that this one is blocked, this one is blocked, and then these are not blocked, okay, then it means that, signal types of 1 and 2, well, I will ignore them, okay? That's what we want. And when you send a signal, there's then sometimes you want to, so when you send a signal, for example, you run a program, like especially when you're writing, say, like a process that forks multiple times, then you're looking at, your like the single process that you have becomes at least like a family of processes, right? And when you press Control C, what you want is you want to kill not only the parent process, but all the children that's coming out of this. Okay. And so for this, we have the concept of a process group, meaning that for each process, we not only have a process ID, PID, but we also have a process group ID. Okay. And for example, imagine that imagine a case where I have a foreground ground job, and then it forks and it creates children. In this case, the PID will be different for each of them. So it's 20, 21, and 22, but the process group ID will remain the same. Okay. And you can set this, using the proper system commands. And in shell, whenever you run a new process, then everything that forks from that has the same process group ID. Okay, and in that case, when you send a signal that's directed to a process group, then it is the signal is delivered to each process that is a member of the group. So if I send Control C here, okay, then this signal is not only set for this foreground job, but it's also set in this child and in this child. So you have these signals basically issued in all of them, and it will basically quit all of them in one batch. Okay. And you can see that we have, these are the basically different functions and system calls that you can get the process group of the current process or change the process group of a process. So the most basically common signal that you use is this, kill program, and this is like it's a system, basically systems program. But what it does is it sends an arbitrary signal. So when you call this from your shell, it sends an arbitrary signal to a process or a process group. Okay. So for example, in this case, I run basically a particular process, and then it creates these children like with the different process IDs 8 and 9, but their process groups are the same. Okay. And then what you can do is when you can, if you want to kill one of them, okay, then you can send this kill minus line, and here basically 9 is this says that this is k equals 9, which is this is the kill signal is the 9th bit in this signal vector. Okay, and that's what it says. So by changing this, you can actually send different signals to the same process, or you can look at the process group, and for the if you send the sig kill, then this is delivered to all the processes inside this group. Okay. And of course, we can send these signals from the keyboard, typing Control C or Control Z. It's essentially sending, sig int or sig stop to every job in the foreground process group. Okay, and this is basically what's happening in here. And you can see then their status with your PS, okay? And you can see, for example, when you do this again for PS, you should read the man page. I would say this is very helpful for you. Read the man page, and for example, you can look at this stat, which tells you the status of the process. And for example, this capital S means it's sleeping. You know, the small s is say this the session leader for that one. You know, T means stopped, and R means running, and etc. etc. Okay, so you should read the man PS for this. Now here is some like simple code for this, and you can see that in this particular code I am forking, okay, and so I fork like create and children, okay, through this loop, okay, and all the children run in this infinite loop, okay, and after that for each of the children, then I send kill to the here's the PID, and you send sig in. This is the macro for that particular one, okay, and then for again for our case, this is where the parent waits for the child status, and from the child status you may realize that like that's the child, like you will see that this particular line that the child will be terminated abnormally, okay, because since when it's killed by SIGINT, then it's not a normal termination, and you will see this happening. You will fall into this else part. So when does the signal handlers run? Well, you remember that when we are in an operating system, we have these different processes, and with these processes you have these process A and process B. They run concurrently, and you run process A a bit, and after that then if you want to switch to process B, then you basically make a context switch, okay, and then run process B. Now this is like at this very point, okay, then I run, this is where I run the signal, okay, uh, handlers, okay, or this is where like this equal to where the signals are received, okay, so right before the context switch, okay, this is so it means that when you send a signal, it doesn't immediately stop the other process, because this imagine with process A, it may have sent the signal here, okay, this is where it sends the signal, and but this one, and but it will continue to run, okay, and only when I decide to make a context switch to process B, okay, then before executing with whatever that instruction, that the current instruction of process B, the kernel checks, and if there's a signal that is pending, then it runs the corresponding signal handler, okay. So essentially what it does is, when the kernel is returning, okay, from another exception handler and is ready to pass control to process B. This can be, remember, this can be a context switch or whatever it is, like whenever you want to execute the new process, then the kernel checks PNB, which is you check and pending and not blocked, okay? So when I look at this is just bitwise and. So if you have a signal that's pending, and if it's not blocked, then you have a 1 for that particular case. So in the end, what you do is the PNB, okay, this is essentially tells you the signals that are delivered to you and which are pending, but also not blocked, okay. So if PNB is 0, then you move on to the next instruction and you go ahead with the execution of your process. Else, which means that you have a signal to be handled, then you start from the least non-zero bit in the PNB, okay, And then with that one, then you force the process to receive the signal, okay? And when it receives, this is basically what we will see how it happens. And when it receives, it triggers some action, okay? And after it's done, it moves and then it repeats for all the non-zero k in the PNB, okay? And only after all these signal handlers are run, then you pass the control to the next instruction. So this portion is basically loops over all the signal handling, over all the pending signals that we have. So as I said, for each signal type, it has a predefined default action. Okay. So even if you're so far you have not in your code, you never, you didn't even knew about these signals, right? Yet when you pressed Control C, it's you were able to quit the process, or when you said Control Z, okay, then you can stop this. So in this particular case, like the default action can be one of these. It can terminate the process. It can stop the process until it's started by a SIGCOMM signal, or it can decide to ignore the signal. So these are all the default actions. Okay. Now, sometimes in certain cases, when you have a you want to install signal handlers. A signal handler means that when you receive a signal, what you want is I want this to happen, okay? Because a signal handler is essentially your way of reacting to asynchronous events in the world, okay? And this is the general way of inserting a signal. This is again, we have this signal function here. And in the signal function, you tell the number of the signal, okay? And then you define, you give the function address of the handler function, okay? And that's it. And so with this, for this handler, you can have some certain values that's defined. You can, if you type in sig ignore, then it means that you ignore the signals of that signal, okay? Or you can signal default DFL. It means that sometimes you set a certain signal for that one, but sometimes you want to revert back to the default action, and this basically does that. It's for that particular type of signal, then it executes the default action. Otherwise, you have this handler, and this is, remember, this handler, this is a user function, okay? So this is your function that you define, okay? So this is basically given as the address for that one, and when that process receives a signal of that particular type, of that number, okay, then that particular handler function is executed. So this is called actually installing the handler, okay, and executing this handler is called catching or handling the signal, okay. And when the handler executes its return statement, okay, then the control passes back to the instruction in the control flow of the process that was interrupted by the receipt of the signal. So here's a simple example. I have main here, okay? And in the main, then I install a signal handler for SIGINT. What this means is, when you press Control C, then instead of executing the default action, it will execute your handler function. And here we say, we say signal, and for SIGINT, run this function. It doesn't have to be this name. It can be bool or whatever it is, okay? And then after that, we just wait here, okay? And here's the function. As I said, this is your user function. And when you do this, you may just loop, you may get into an infinite loop here. It doesn't matter. Then here, when the user presses Control C, okay, then you can say, well, so you think you can stop it with Control C? Well, you wait for a second to make sure that the guy understood that, this is really optional. And then you basically write your like, well, and then, okay, and then it exits. You don't have to exit, by the way. Okay. This is something that we just did out of nicety. Okay. You can actually have your signaling handler just do this. And as I'm ashamed for this, but, at one point when I like sometimes you can just relaunch your program. Okay, you can maybe go back to a certain function. You can reread the same thing. So after the signal handler, when somebody presses Control C, for example, you can have a reboot of your whole process. Okay, you can, for example, you can execute. You can do whatever you wish. Okay, you can have that is something that's runs forever. Okay. So as I said, the single handler, basically it is run right when you are exiting, when you are leaving the kernel mode and right before the next instruction. Okay. And so this is like, this is important. And not the like, so it's, if the, as I said, if the signal is pending, then it has to be a little bit careful, right? Now, when you look at this, you can see that I'm actually running my own function, but this function is being run like a user function. Okay, it's like, at that particular moment in time, I said that, make a call to this function. Okay, which is fine, but you have to be very careful. And the reason is, when you're making a function call, that's especially in the user space, it means that you can screw up your stack. Okay, because stack keeps track of where you were in that particular case. So, and we call this the state of the stack as a as a context. So you have to be very careful on not to screw up the stack that just because you're executing your signal handler. Okay, so what you do is you modify your stack as if you made this special subroutine or function call. Okay, and then when you're returning from this special subroutine, then you basically make another system call to restore it to the original state. So you can see that there are some, like I have a link here if you're more interested in this. And I suggest this is really good reading for that.
Hocam,
So,
can I interrupt quickly?
sure.
We were discussing some details in the chat, and I want to ask if the analogy with a piano is correct when it comes to signals. We can't really push the same button again without releasing one.
Right.
And let's say the handler is something inside the piano, it might vocalize the sound or not, but without releasing the finger, we can't really send another pushing button effect with like a signal.
Exactly. I mean, I make it like this. It's like a, the electric switch, right? It can be on or off. So it's you're basically setting the switch to one state, and after that, if you set it again, then it will, or it's like the, if you wish, maybe the elevator, floor numbers, right? You push once, okay, and like a lot of guys don't realize it, but if you push the same floor 10 times, it doesn't have any effect, right? But you never. So this is the same thing that you signal. You're sending a signal to the and as for the elevator, when it gets to the proper floor, then it clears this out and it moves on to the next one. That's the same thing. So maybe the elevator, floor signals is floor basic numbers is a much better example. Okay. So with the signal handler, as I said, it uses the user stack. Okay. And what the kernel does is the kernel basically has to push the handler functions activation or stack frame on the stack. Okay, this is don't get really confused. This here the stack is growing up. Okay, so imagine that on my RSP, this the top of the stack here, and I have this current, RIP, the instruction pointer to IP current. So let's say that, at this time I have I have a signal and I want to process this. And what you do is, for this particular case, like here, you modify the stack frame, okay? So you allocate some space for the local variables that may appear in your handler, the parameters, and you also basically push the IP current, which is the return address, from the handler, right? So that's basically, and then within this, you execute this, and then when the handler returns, you basically go back and you make sure that you return to your current instruction, basically at the proper place. And after when I'm running this signal handler, you prepare this stack for this, and you set the instruction pointer to the address of the handler, and it will execute this, and only after that it will return, and it will return to your current instruction that's right there. So note that things can get messy in this case pretty easily, which is when you're running handler, okay, which is which can be another user function. It can actually be interrupted by other handlers, right? Okay, because this is the same. You're just running a new function, okay? So what can happen is you have your main program here. Your program catches a certain signal, and then you start running this basically for the handler for signal S. You start executing. It's not finished yet. Okay, maybe you and at this time you have a control. You have a context switch, and you come back, and another signal, say signal T, is basically caught. Okay, and that time, then you may say, okay, I will now execute the control handler for T, the new one, and you'll execute this. It will come back. You will continue the execution of handlers S, and only after that you come back and here. Okay, so this can be happen. This may happen, and it can happen, for example, and you have to deal with this. And for this, imagine, for example, when you press Control C twice, okay, which happens all the time. What do you want? Okay, are you like this is just like the it's you want to make sure that after handling the first one, Control C, and before you're done, if another Control C arises, what do? Well, to deal with this, you have to be you need to use this blocking and unblocking basically parts. And the first thing is there's an implicit blocking mechanism, and which is that if you're executing a signal, okay, and if you receive the same signal again, then it's implicitly blocked. So if I'm handling Control C, and in that function, if I receive another Control C, then it's blocked. Okay. So if this means that the SIGINT handler cannot be interrupted by another SIGINT. Okay. So that's, and so this is by default, this is handled. Okay. But sometimes you want to also can have more control, and for this you may have this explicit blocking and unblocking mechanism, and which you can do using sigproc mask. This is the signal mask function, and with this function you can decide, if you remember, like we had this pending bitmap, and then we have this blocking blocking bitmap, right? In the blocking bitmap, then you want to change these bits so such that you can block this. And it has a number of functions. Again, remember that this is a data structure in the kernel space, and hence any update has to be done using a system call. So here we have a number of supporting functions like sig empty set, which creates an empty set with all zeros, or you can have sig fill set, which adds every signal to this, or sig add set or del set. So you have to read this. With these, you can actually set your blocking bitmap to whatever you wish. Okay. Now, when you're writing handlers, you have to be careful because any data structure that you have in your handler, you know, they may be they will be being updated concurrently with the main program. Okay, say that for example you have like in your program, and we will learn this more in detail in our next topic, maybe starting next week, which is like say that this is your address space. Okay, and in your address space, say that I have a variable here. Okay, and here's my main code. Okay, and my main code is said reading and updating this value, and in this, and then you have this code for your handler. Okay, and after as you're updating this, then the handler may be called. Okay, and this update, and we will again see this later. For example, imagine that I have this particular data structure. Okay, and in this case, let's say that its value is 0. Okay, and my main wants to increment it by once. Okay, how do you do this? Yeah, well, you have to do it. Requires at least 3 instructions. You read the value from the memory into a register. You update the register by 1, and then you write it back. So it will require 3 instructions to update this particular value to 1. But now let's consider the following case. This main program, let's say that these are the 3 instructions for a particular that. So this reads, this updates, and this writes it back. Okay. Now let's say that after executing say that after executing the first 2, you read and you update, then at this point we had a context switch, and then we had to then jump to the handler. Okay, now when and let's say that my handler is also wants to increment this very same data structure by incrementing with 1. So, and then again we have these 3 instructions. So it will read it, update it, and then basically write it back. So now it becomes 1, right? And then the handler returns. We come back, and this will again write 1 here. And what will happen is instead of 2, you will have 1, and we will see that this is what we call a race condition. And hence, when you are, if you in your handler, if you are going to update any global data structures, which are basically which may be updated by your main program, then they can become corrupted. Okay, we will see much in detail about what this problem is later. And as I said, these like pending signals are not queued. We already know this. So what this means is, for example, you cannot use the signals to count events. Okay, and for such as your child's terminating. Okay, so for example, and for signals, sometimes you have to wait for a signal, which is like sig suspend. Then what this does is it pauses the current process until that particular until a set of signals within this set basically have been received. Okay, this can be a sig child, which tells you the information that your current one of your children has died, or etc. But you cannot use them to count things like your child, how many children you have terminated yet. It's because whenever your child dies, it will set the signal to say 1, and before you process by say incrementing your terminated children count, you may actually receive another signal from another children terminating, and hence it will get lost. Okay. Any questions so far?
Hocam, we have a like kind of a hard question, we thought. So if we have these signal handlers being executed one by one, starting from the least significant bit, say we have this signal kill at 9th bit. If we have a handler for, let's say, the signal 5, and it just runs an infinite loop, we may not get to the signal kill because we are still dealing with the handler for 5. How does it get interrupted and transformed to the signal 9's kills handler? Who handles that?
That's a good question. But the first thing that I would say that I would check for the other like the bit numbers, okay, and that's again like you have to be a responsible programmer to make sure that your handler is not running in a infinite loop. But these are things that you should go ahead and just try, okay, and and see what happens for yourself. Okay.
So if it works, in that case, we may have overridden the handler for signal kill, which should not be possible.
Well, for certain ones, you are not allowed to do them. So you cannot replace the handler for all the signals. Okay. For example, like there's a signal handler for example, for handling the interrupts coming from the timer, which is sig timer. Okay. And if you disable this, what it means is the operating system has no way left to interrupt the current executing program. So all those things are actually not allowed. Okay. So you have to read the fine print.
I will try it and see my findings and report back to you.
So this is like this.
I think that kill will still get delivered, but maybe later on, because when you're in a signal handler, that doesn't mean that your process suddenly becomes uninterrupted, right? Even if you're handling a signal, your process is going to get paused, maybe rescheduled later on, etc. So at the time it gets rescheduled, the system will see that there's a pending signal 2, for example, and then it's going to put the signal handler 2. Next time, oops, signal handler 3 is here. Maybe I'm going to put signal handler 3, etc. So even if we had, like, if we replace every signal that we can with infinite loop handlers, I think the process will still be able to receive all of them. But it's worth trying, definitely.
That's correct. Like for example, as I said, if your handler is running on the signal 3, okay. It will it will get interrupted by the timer. When it comes back to context switch to execute the rest of your handler, then it will realize that, for example, the kill signal is there eventually, and then it will then execute this, which will kill the process.
Okay. Yeah. Okay.
Okay. Thanks, Deniz. So let's have a break here, and we'll continue in 10 minutes. Okay. Do you have any questions about signals? No.
If no one has any, I have one.
It's
not exactly a question, but it's more like a motivation to learn more. Let's say. So signal handlers execute in user mode, right? So our program, let's say it's crunching some numbers, doing some stuff in user mode, like we always do usually, and then it gets signaled. Okay, perfect. We put the signal handler on the stack and then schedule it, and then the signal handler runs. Great. But let's say we are sleeping in a system call. For example, your program is waiting for some data from a file. Could be a network socket. So right now it's sleeping in kernel mode. If the process gets signaled while it's in a system call, while it's in kernel mode, then what should happen? That's the question. Because it's not easy to just, we can't just run the signal handler in kernel mode. We can't go back to where we were in the system call, etc. So it's kind of complicated. I mean, Just something to think about or learn about for the students.
Yes, but when you're sleeping, you cannot make a context switch back to the process.
Uh, yes, you can't just.
So
I mean,
you
there are
never
multiple things you can do.
you will never have the chance to process the signal
Yes, so
if you're blocked.
you need something. Well, there needs to be a mechanism to handle it. It's a special case kind of thing.
Okay.
It's something interesting, in my opinion. Something that I didn't think about when I was a student, but then you write some circuit code and then it happens.
Oh yeah, that's very good. It gets much hairy.
Yeah.
Okay, so let's move on. And okay, so a lot of the things that so far we have seen some forms of interprocess communication that's appearing, and like we have seen unnamed pipes, we have seen named pipes, okay, and we have seen signals, okay. But in all these things, like it's this communication between different processes. It's always it's not easy. You basically update some sort of a kernel space structure and then have this kind of indirect communication. But sometimes what you want to do is you want to have much closer cooperation. And like, for example, and this is where we have this shared memory. Like imagine, for example, your browser, okay? In the case of your browser, and this is again, this will be, I may share the link for Chrome, in which case each tab is running as a each tab is running as a separate process, right? So sometimes what you want to do is you want to have really immediate sharing of data between different processes. And what I'm talking about is large amounts of data, like, you say one process is downloading some images and the other process is displaying them, okay? So in that case, sending them through a pipe or like using, as I said, or other things is very it's not fast enough, it's not sufficient enough, and etc. So for all these things, we have this virtual memory space, okay, that we can share among multiple processes. So in the shared memory, what we do is, remember that we have like process A and process B. Usually these squares are completely separate. So as default, they live in their own worlds, right? And they never get to see each other. In the shared memory, we define a portion of the memory in the physical space that appears in both processes virtual address space, okay? So you no longer, you don't rely on any kernel space communication, but your own address space, whatever like process A writes into this shared memory will become immediately available to process B or vice versa, okay? So this is what we call a shared memory, and this is very useful, but it's also it's easy, but it's also very tricky, and you can actually see that we will have a whole class of problems called synchronization problems, and it's actually very tricky to handle this properly because of this. So the idea is pretty simple. We know that when we have these different processes, and your virtual address space, here's your virtual address space for A, and here's my virtual address space for B, okay? And these are these are different pages. These are, virtual pages, okay? And what you do is for these pages, usually, here's my physical memory, okay, and physical address space. In this case, you have these different pages which are being mapped onto the physical memory, okay? And with this mapping as default, if a page in my physical memory appears in process A's address space, it shouldn't appear in process B's address space, right? And this is just a mapping through the page table. And but if you make the, so what this means is the operating system can say that, I will map this particular page onto this physical page, okay, and this one to here. And if you can also map the same physical memory pages to process B's virtual pages like this, then you can see that they are now both pointing to the very same physical memory. Okay, and they may appear as different addresses. For example, for this one, it may appear that the space is between, say, 0x3 30,000 to 50,000, and in process B, the same physical memory may appear as a region from 50,000 to 70,000. Okay, so this is how it works. And the general idea is that you have one process which would create or allocate a shared memory segment. Okay, so you declare this, you declare the size, you declare the access permissions at creation, and then it attaches this shared segment into its current data space. Okay, and we'll see how you do. And then, basically, if necessary, it may also initialize this shared memory because it will be shared by someone else. And then, once created and if the permissions are set, okay, then other processes that are completely different from the or even unrelated from the current from the original process can gain access to the shared memory and then map this into their own data space. Okay, and then each process after that, then they can access the shared memory relative to its attachment address, and for each of them, the mapped memory address appears to be no different from any other memory space that it has. Okay, so here's the shared memory basically usage in the POSIX standard. Remember, the POSIX was kind of a standardization. It's a standard for operating systems. It defined a set of system calls which will accomplish certain things. And this is basically how it handles shared memory. What this means is, if any POSIX compliant operating system will provide these system calls. And if you learn about them, then this will, for example, if in Mac OS, this will also be supported as well as in Linux or any other POSIX compliant operating system. So here we have our process A. And the first thing that we do is that we have this shared memory get. This creates a shared memory segment. And you have a key which we will use to basically restrict access to this memory segment. And you say, what's the size of the memory segment and what's the permissions for this? It's like creating a file, okay? And you get an ID. And then once you have this, then you say that once I have this, I want to map this, which is called attaching your shared memory attach with this ID, which you get from this, okay? And don't worry about this. And then you attach this, and then what you get is you get a pointer. Now this address points to the shared memory segment. So this first one in the physical memory, you say that like you create a segment here, okay? And then in the second one, it's attached to your own address space, meaning that if this is your this is your physical memory, this is your virtual memory, and then in here, maybe in your your heap, you say that like this particular address is now mapped to this segment. Okay, and then after doing this, now you can write or read from your shared memory. Like and writing into this shared memory is simple as setting star address to 1. Okay, and once you're done, you can then detach the shared memory. So this is basically for process A, and then process B or C or D, whatever like numbers. Okay, you can have an infinite number of processes here. Then you can use this existing segment. And the way we do this is, again, you say I want to get a shared memory, and here's the key. Now this key is should be the same that's being created by the original one. Okay, As long as you have the same key, then you can have, if you know it, then you can access to the very same shared memory region. Okay, and then you get it, and after that you again attach it with the same ID, and you get an address. And after that, you can then, for example, read from this memory or even write it. It doesn't matter. And then when you're done, you can then detach the shared memory. Okay.
Hocam,
So
I'm sorry if you already mentioned that, but what kind of mechanism do we use to transfer these keys between different processes? Did they need to have some sort of inheritance or that kind of relationship, or how was it?
In your code, you should write this. Okay, so in your code for process B, you should use the same key. Okay, so you cannot know this unless it's coded. You will not have this unless, of course, you read the key as an argument for your program.
Yeah, we don't do the exchange during runtime. I was confused
No.
for a second, so yeah, it makes sense. Sorry.
You don't do that.
We determine it.
Exactly.
We could do it
Okay.
if you like. Of course. It's just a string.
Mm-hmm.
So you could send it with a pipe, for example. But it's
Right.
up to you.
Yeah, actually, yeah, we could do some allocation or something during runtime too, but yeah.
Okay. So, for example, what you can have is, we will see this again in later. There's a producer consumer problem. You may want to have two different processes, one producing some data, the other one producing consuming this data, and they may be writing and reading from the same buffer. Okay. And this is an example is that, you can have a print utility, which basically places the data into some shared memory region that you can print, and then the printer then fetches this data to print and maybe clears it out. Okay, so there are a lot of similar problems. And here's for example, server code for the producer. Again, you can select, so here's the key. Okay, if you know the key, then you can write your own program and then basically, attach this. So any process who knows this can attach this. So for the server, you can imagine that this is, for example, your print server, okay? And so you create the segment, okay, with the key, okay? And you say that the size is, say, 27 bytes, okay? And this is creation. Again, these are the properties for this. You get your shared memory ID, okay? And then after that, you map this into your own address space. You use this shared memory ID, and now this gives you a pointer in your address. Okay, and then after this, well, you have your space. Then into this shared memory region, then you can do whatever you wish. You can read or you can write. For this case, in our server, you're just outputting some data. You set set this to S, and then you write into this you remember we had this 27. The size. This is the size of our shared memory segment. So you write all the characters from A to Z. Okay, by incremented by one, and then it sleeps. Okay, it sleeps until this until remember in my shared memory segment this is pointed by SHM here, okay, and my S basically goes through here and it puts A, B, C, D, blah blah till Z, okay, and then it waits, it sleeps until the first character is star, okay. Now we can see that as it is, this server will sleep unless there's some other process which changes this shared memory here, okay? And when it's done, it detaches. Now let's look at the client code. So the client has to know the same key. That's 5678. Again, it gets with this key, then it gets it, okay? And it gets the ID. And then it attaches this shared memory ID into its own data space. So now this pointer points to, again, if you print this address, it will be different from the address that you see here. Okay, so this is the address for the shared memory in the server code, and this is the one in the client code, and they will appear that they will be different. Okay, and in this case, for the client code, for the consumer, well, let's say that in this case we start from that, and then until Z, you read and you print this on your screen. Okay, and when you're done, then in order to signal that you basically for the server, you change the first character. Remember that this was our shared memory region, which we had A, B, C, D, etc. Then you change this, okay, to a star, okay, and you exit. Now let's come back and now look at when you look at here, the server was running this while loop, okay, and checking this star, okay, and when the client puts a star here, then it exits it, it detaches, and the server ends. Okay, so this is pretty simple, and I think I will leave this to Onur because he will be trained. This is where we have a shared memory example for currency exchange where you can buy and sell different currencies through using the same structure. So I will skip this, and I believe Onur will be doing this on next Monday's hands-on lecture. Okay. And usually, when you want to generate a common key, instead of putting 5, 6, 7, 8, there's a, F token function, which can return a key based on a path and an ID. Okay. And so with this, then you can use this in basically subsequent calls to other ones. Okay. And note that this function will return the same key value as long as the path is the same and the ID is the same. Okay. And in this particular case, there's again some so you have to be careful with its low order 8 bits of this ID are significant, and anything beyond this are not used. Okay. So for the shared memory, its advantages is obvious. It's good for sharing large amounts of data. It's immediate, like very fast, and it's immediate. Okay. So whenever you're running process A and process B, then what you do is you, whatever you like, when you make the context switch, you immediately see that that's available. The main problem that we have is there is no synchronization, meaning that, how do you know that the process A finished writing its code before, the other one is read? I mean, look at, let me just go back to our example here. Okay. So for example, let's say that, in this particular case, my server, okay, is writing this data, okay, and then it will wait here, right? Now let's say that before writing all this data, so it writes so ABC, okay, but before this, maybe it stopped at K, okay, and here we had a context switch, okay, and so in this context switch, then we switch to client code, okay. Now the client code, then it will read this and it will print this. So obviously it will print everything else, but there's a lot of garbage here after K. Okay, so it will print this whole thing, and then it will set that I'm done. It will set this to a star. Okay, so in effect, basically, this client code has received only part of the information. It provides a lot of garbage code, garbage data onto the screen, which is wrong. Okay. And then after, when we make the context switch, then the server code will put the L to Z here, but which are never used and printed by the client. It will come here, well, it will see that it's already printed to star, and then, well, detaches. So this will lead to a wrong execution, which can happen. Okay. And as Murphy's rule, this, if something wrong can happen, it will happen. Okay. So we will see how we can deal with this. And then, a lot of the shared variables can be violated, okay? And we will again be covering this in the synchronization part, okay? And it will be persistent until reboot and hence needs cleanup. Now there's another alternative to this, which is called basically a memory map system call, which is actually does the same thing except that it maps this region, it maps a file into the address space of the caller, okay? And it will make things, the data to be persistent. Okay. Do we have any questions? No? Okay. So before I move on, let's open our poll about signals. Okay, now that we're halfway, so this will give us a 5-minute break. So I will run the poll and you will have 5 minutes. Okay. So what's the time? Time is 5:04 and launching the polling. Okay. So you have 5 minutes. Okay. Now, let's look at another type of IPC, which is called memory mapped files. Okay. Now, this is interesting. It's actually more flexible than the shared memory. And what you do is you link the file into your address space. You map it into your address space. And once you do that mapping, then you can manipulate the contents of the file by updating the memory instead of the regular file system calls like open, read, write, seek, and etc. Okay, so what this is interesting, and if you think of it, remember that in the case of a virtual memory, okay, if you remember, at the beginning we have the code section, right? The code of your, and then this code section would have all these different pages, and initially the code section would be mapped onto blocks of the executable, which is on the disk. So this is your disk, okay? And what it would do is, whenever you try to access this one, if there's a, it would create a page fault, and hence it would copy this into your main memory, physical memory here. And then it will be mapped to this, and then it will then execute it, okay? So in a sense, this is what we mean as memory mapped files. This already exists in our virtual memory concept because we are essentially mapping our disk, the files on our disk, into our address space in our physical memory. Okay. And then we can share this because, our files already have all these ownership and protection ones and etc. So, and the nice thing is the contents of a file are non-volatile, meaning that even if all the processes that accesses them are closed, the file will nevertheless remain on the disk. Okay, so this is different from your shared memory. For example, in the case of a shared memory, it will remain in the main memory, but when you reboot, the contents will be gone because it's never written back on the file system as in a persistent way. So this is again these are the system calls to use a file as a shared memory. So this is the memory mapping, mmap, okay, and it has these arguments, and this is start is the address for attachment. It's usually set to 0, which basically directs the system to choose a valid attachment address. Length is the number of bytes to be attached, okay, and we have to make sure that the file size should be less than or equal to this, okay, because you may want to map only a certain portion of the file, and then the protection is used to set type of access, okay, and then we can have map shared to share mapping. Otherwise, when you map this into the memory map, everybody may be mapping in different case. Otherwise, it'll be isolated. And then we have this FD, which is the open file descriptor, which means that you have to open a file first, and then use this mmap to share it to map this in your physical memory. And the offset is the starting position for the mapping on the file. Okay. And well, if when successful, then it returns an address, a pointer to the mapped memory object. Okay. And else it will return -1. And when you're done, you're supposed to do an on map, and which is automatically called when the process quits. So here's the same example again, which I will leave to Onur Hoca to basically work through this as a hands-on thing. And in this case, in that currency exchange example, we were supposed to keep track of how much dollars do we have, how much pounds do we have, how much lira do we have, and all these different processes that were running concurrently. They would then attach this, they would use and update these values. And what you want to do is at the end of the day, you want to write them into a file. And in this case, we will say we'll use this exchange.dot to basically store this data. You open this, okay? And then after that, then we make this memory mapped, okay? And this is the size of the region that we want to map, which is in this case 4 times the number of like a structure of this currency structure, okay? And then as a result, what we will get is we'll get a pointer as struct currency pointer, okay? And after this, well, you do whatever you wish here, okay? And once you map this, you can actually close the file descriptor, okay? Now that it's mapped, and so it means that, and the nice thing is when you update the contents of this, you update them as if they are at this point, for example, when you do a buy or sell, in here, you're actually updating the data structure which resides in the file. But you can see that this is much more convenient than basically doing a seek or read or write. This is like, just, memory, as if all these data structures are in your memory and created by you, okay? And finally, you do an unmap. And again, with this, you can here's another application of this. You can read from a file again with mmap. You open your file, whatever it is, okay, and you then map this and get this pointer. Once you have this pointer here, this map, okay, then you can update this any way you wish, okay? And then when you're done, you just unmap and you close the FD, and that's it. Now you updated your file, so we can see that this is really convenient. So with all these being said, this is just forget it. This was hidden, but now we'll move on to other IPCs. Another one is called message queues. Now we have already seen that, like when you have these two processes, like here we have the sender process and receiver process, then usually in the case of, we have seen like the case of a pipe, right? And the pipe you read and write and here. But when you're reading and writing, we could never be sure, like when you're the sender and it tries to update this pipe structure, then you have this issue that I want to remove my background because you cannot see my hands. Okay. So when you have this sender and process, receiver processes, when the sender wants to write some information, you cannot know whether it has completely written its whole data before this guy tries to read it, right? And so this is a major problem. What you actually want is, I want to write the whole data in one batch in an atomic way, and I want to make sure that the other guy cannot read it before I have completed my write process. Okay. So for this, we have these message queues. In the case of a message queue, basically the sending process, it places a message onto a queue. So you have these messages, okay, and you put them onto a queue, which, on this slide, which you insert from one end and then you remove from the other end. But these items are inserted or removed, or inserted or removed in an atomic way. You cannot send half a message, okay? And moreover, in this case, for each the messages, you can also provide an identification or a type, so that the receiver can select to receive only the appropriate message types. Okay, and again, for with the other cases, the processes that communicate through these message queues need to share a common key in order to gain access to this queue in the first place. And the messages, its length is explicit, and it may have basically different types. So the way it works is, again, like with the shared memory get, and now we have this message queue get. Okay, this is you define, like you get your message queue, and then after that, then you do a message send or message receive functions. Okay, and when you do them, you can have like two different execution. You may have a non-blocking message, which may mean that you when you call the message send or message receive, it will return immediately. Okay, so this is called non-blocking, meaning that you imagine you want to receive a message and there is no message in the queue. Well, it will return immediately with no message, and so you can handle. In a blocking case, if you want to read a message with message receive and there is no message, you'll get blocked. Okay, and so this is the main thing, and this type of basically blocking and non-blocking types is common for a lot of these inter-process communications. So here's again some sample code, and all these codes are, by the way, are available on Onur Hoca's page, and which I will share, which is also available. I think Onur Hoca must have shared, but it's also available as the last slide on this lecture. So here we have again a key, and with this key, then you create a message, a queue with a proper ID, and then, well, you define your message as such. So this is my message structure, and here's the type of the message, and here's the content. Okay, and now if I want to send a message, you set the type, and in this case I'm just sending it to type 1, and here's my text. I copied it, and then after that you send your message. So here's the ideal. You may be dealing with multiple message queues, and then here's the message and with the length, and that's it. So this is the part where we send a message, and this is the receiving end. Again, you use the same key. You basically get access to the message queue, and then you receive again here with this particular ID. You say that I want to read a message of this type. Okay, and in this case, this type should be well. In this case, when it's as such, you may be reading anything. And in this particular case, the message of type 1 is received from the queue with this text stored in that, and you can then read this out from this structure. Okay. So with the message queues, they are more versatile than pipes because pipes are really primitive. Okay, and we can basically transmit messages. It's like an atomic thing. You don't have to worry about these partial messages being sent or received. This is in the case of a regular pipe, named or unnamed pipe. This is a major problem. Okay, that you have to deal as a programmer. And in the message receive, when you're defining the type parameter, there are basically three basic modes. Any type means when you set the type parameter to 0, it means that I will receive any type of messages. Or you can say if the parameter is greater than 0, then you're looking for basically specific message types, or sometimes you may have a minimum typed message, like basically like a priority. That's it. Okay, so you can use the message type to specify the priorities or urgency, or sometimes the designated recipient, because remember that with this message queues here, okay, and again you can have basically multiple processes, P1 and P2 may be inserting messages into the queue, and then you may have other processes, say P3 and P4, maybe reading from this. So you can actually use the message type to say that if P1 wants to send a message to 3, maybe it will set its type to 3, and then the P3 will receive it, and P2 may communicate with P4 as such. Okay. So of course, like you have to deal with yourself. The kernel does not provide any recipient to the specification, and there is again no broadcasting, meaning that when you put in one message, it can be received by only one process at a time. This is again the same thing with the pipe. So the time is up, so I will stop here. The last, I have a couple of other IPC methods like circuits and remote procedure calls and other things, but we will see this, we will cover this next week. If you have any questions, please let me know. Otherwise, I will close the session.
Jump for the quiz question. Why is the local variables cannot be modified or corrupted?
It's because by definition, the local variables are allocated on the stack, right? So if you update them, well, as a matter of fact, you're updating them is when you update them, it cannot be accessed from the main routine. So hence it cannot be corrupted, okay? Because a local variable in a function is a local variable because it is allocated each time that function is executed, and that those local variables are discarded when you exit, when you return from that function.
Okay.
Is that clear?
Yeah, that was clear.
Okay. Any other questions?
Hocam aslında doğru da düşününce directly we cannot directly manipulate local variables. Maybe we can do some pointer indirection and update the local variables because the function hasn't returned yet. Am I thinking right?
Oh, I mean, even if you run, you take the following keys, even if you try to run the same call, think of a recursive call. In the case of a recursive call, although you're calling the very same function, you will, the local variables will be instantiated separately for each instance of the function, right?
Yeah, if we have a pointer which is pointing to a local variable before the signal receives, then if we update the global using the global pointer, then it will be changed. before the signal handler.
Well, I mean, that doesn't make sense. It would mean that, you know, we can just then point to anything on the stack, any address, and then you modify this. So that's not going to work.
Yeah, but the question asks the other thing.
But whose
Okay,
local variables is also a question, I
in
guess.
other questions, okay, you tried your chance. Okay, in other questions? No, okay. So I'll see you next week then.
Görüşmek
Görüşürüz
üzere
hocam.
ve herkes